Hi, so I thought I'd talk a little bit about charge controllers actually. Now, charge controllers seem to be immensely complicated, and I guess they are when you sort of get that black box and have a look at it and you start pondering what you can do with it. It's quite complicated. And it's like a computer. When you think about a computer, it's a complicated piece of equipment. But at the very basics of it, of course, it's actually really simple. All a computer is doing is turning a switch off and on. There's just a lot of them. And because there's so many of them, it gets quite complicated to look at it from the outside in. Now, it helps me when I'm trying to understand something to make comparisons between things, to give me links between things so that I can see where they came from, and also to have a bit of a look at the history of things so I can see how it developed. When I look at their thing in that way, then it helps me understand the mysterious black box in front of me that really is a huge book to read through to even learn how to turn it on. So that's what I thought I'd do. I thought I'd have a look at some of the basics of charge controllers, where they began and how they've developed, and then come up to charge controllers that we're currently looking at. So I've got a couple of bits of equipment here, and we're going to have a close-up of it. So what I've got here is a solenoid. It's a coil of wire. I'm going to put a current down. That creates a magnetic field, and in the centre there is a steel rod. That'll get magnetised, and it'll be pulled into the centre of the solenoid. But this one I've attached to a rubber band. So it is a solenoid on a spring, and if I put some power in there, it jumps forward, take the power off, it springs back. Now, that might not seem mind-boggling to you. It is to me, because that is the basics of the very first charge controllers. They're electromechanical charge controllers. Now this one is just a solenoid, moves backwards and forwards. But if I put a switch here and attach the power to the switch, when the solenoid moves forward, it will turn the power off. As the power goes off, it springs back, which turns the power back on. So if you like, that's a way of sensing the power input and making sure that the spring setting won't go further than a previous voltage. Now that's exactly what I've set up here. So all we've got here is a solenoid. It's in a different arrangement. There's a circular coil here, the solenoid is a straight bar, there's a couple of magnets, so when I turn the power on, it will be pulled towards the magnet, and here I've got a couple of bits of metal that intersect the power. So as that pulls across, the power will get turned off, and then it'll go back. It will self-oscillate. It will self-oscillate at a certain rate. If I just left it by itself, then it would arc and go through a process called hunting. So what you do is across the coil, put a capacitor. The capacitor gets charged, it feeds it. When it breaks, the capacitor needs to discharge a little bit so it can stay broken, and then it will come back. So it prevents that hunting that we saw before. So let me set that up. Okay, it's connected to the power supply, and if I turn the power up, we can see it flickering backwards and forwards, shutting off. Now that's set at 5 volts. So it doesn't matter now what voltage I put in there. At 5 volts, that will turn off. So whatever the input is, the output is going to always be 5 volts. Now I can change that by changing spring tension, changing the position of the magnets, all that sort of stuff, but 5 volts is all that the output will be from that particular electromechanical device. So I actually think that's simple, but really cool, because that stupid little electromechanical device there, the coil and the solenoid, what it does is it regulates the voltage. Doesn't matter what voltage I put in there, the only voltage I can get out is set by the spring tension, and in this one it's 5 volts. So that voltage will now never go above 5 volts. And in fact, this kind of voltage regulator here is what was used for a long time prior to creation of solid state. It was this kind of stuff. Now, these things actually still have use today for very high voltages. Of course they get more complicated, and of course we could use this particular version actually. Because we have a sweeping arm, we could sweep a series of contacts and we could get different voltages out of it, and that's exactly what happens when you do this but have a rotary arm, so you can get a rotation of step voltages using something like that. So that not only is a voltage regulator, it can be a variable voltage regulator just as easily. Now for me that's actually very cool. Now why go about voltage regulation? Because like I say, voltage regulation for me is the very basics of what charge controllers are all about. Charge controllers are all about making sure that you don't put too much voltage into your battery. Now this is set at 5 volts because of the spring tension. Let's say I wanted to charge a lead acid battery, I needed 14 volts. Well, I could change the spring tension so that it had 14 volts. And all of a sudden, I've got a battery charger with charge control. Now, I'm not suggesting people make something like this. What I'm saying is that this is doing a physical job in a way that we can see. The switch, if you like, at the end of here is being turned off. This, if you like, is sensing the voltage and making sure that the voltage is held at a constant. So this performs those functions of sensing and turning off the voltage supply that a simple battery charger actually does. Only that simple battery charger does it with some electronics, and this one is just doing it mechanically. But it's doing exactly the same thing. Now, because any voltage above that is basically just thrown away. What will happen is the coil will get hot. If we don't want that coil to get hot, we have to do something else with it. So I put a capacitor in series to prevent the hunting. If I put a light bulb in, then all the extra energy would go into the light bulb instead of heating this coil. If I put a large resistor in, all of that extra energy would go into heating the resistor, rather than heating and breaking this little mechanical device. And you will find charge controllers that do exactly that. They're called dump loads. They're a bit simpler, but they're exactly the same thing done electronically. What we actually have here done mechanically. What I've got here is a car alternator. Now inside here is a little bit of solid state circuitry, doing pretty much the same thing as that, because this will change the amount that it can generate depending on the speed of the engine. Faster the engine, the faster this turns, the more it generates, and you can get quite some voltage out of this. But of course the main thing you do with an alternator is charge a battery. And if we put more than 14 volts into a lead acid battery, we're quite likely to blow it up. So what the electronics does is controls the voltage in the same way that this did, to make sure that although the voltage here being generated can be quite high, the voltage that the battery gets is within that range set by this. This is set by, actually it's a diode and resistor series that set the voltage. Here we're using spring tension. We can use diodes and resistors to do that, but that doesn't really matter. It's setting the voltage so that the voltage is now independent of the voltage generated. So the voltage generated can rise up above, but the voltage the battery will see is only at the 14 volts. So this voltage regulator inside the alternator is in fact acting as a charge controller. And this is what I mean about these things being related to each other. Now, these aren't very efficient, obviously, because what we're doing with the excess voltage is essentially chucking it away. And of course, that's not great. And the other thing is, of course, it can have a very low voltage, and that low voltage isn't being used particularly efficiently, but the high voltage is chucked away. So the efficient performance of these isn't great. But it doesn't really matter so much in those applications, because you really just want to keep the battery topped up while you're running around, and there's plenty of spare motion to do that, so it's not an issue particularly. It becomes an issue when you're using things where you need to get every scrap of power out of there and save it. So things like photovoltaics and wind turbines, we don't want to be really chucking that energy away. I mean, there are occasions when you do, like if you're charging and you're saving it to your battery bank, then once your battery bank is full, you don't want to be charging it anymore, so you want to chuck it away. And that's part of what the charge controller will do. So when we're looking at voltage regulation, we don't have that extra little bit that's going to be needed to pay attention to what happens at over voltage and, if you like, under voltage too. Okay, that's pretty much enough for one video, I think, because it's already getting a bit long. And the main takeaway here is we're looking at voltage regulation leading to battery charging. And what's happening in voltage regulation is a specific set of functions. It's got a logic to it. And the logic's really simple. Provide a voltage. If there's too much voltage, turn it off. Those logical things are implemented with specific methods of doing it. Now, we used a mechanical method because you can see it doing it. This is sensing the voltage. Once the voltage goes above, it's turning the voltage off. It's performing those logical blocks, but in a mechanical way. Of course, now we do it with electronics and solid state, and we'll be looking at that and where that's developed and why that's developed in the next couple of videos. But all I really want you to get hold of here is that there is a simple function being performed. That function is a logic. The logic can be implemented in many physical ways. I'm going to talk a little bit about concepts here, actually, and some of the guiding principles, if you like. And to do that, I'm going to do some things that seem a little silly at first, a little fatuous. But bear with it, because it'll make sense at the end of the day. Anyhow, having given you that warning, I'm now going to do that stuff. But like I say, I'm being deliberately silly. Okay, so let's have a look at this thing. This thing is clearly a light switch. Watch what happens when I do that with it. Isn't that awesome? It turns the lights off and on. The thing that I wonder is, how do the lights know? When I press that switch, how do the lights know to go off? What is it that tells them to go off? Of course, that's a stupid question, because nothing tells them to go off. It's built so that it will operate that way. But I have a choice when I look at this. I have a choice to either say that I break the wire and the lights will turn off, all part of the system that the lights and switch is. Or I have another choice to be able to say that the lights sense that the switch has been turned off. Now, it makes no sense to say such a thing when we're talking about a single light switch. But actually, that is exactly what we're doing when we're thinking about computing. In the last video, where we're talking about the early days of voltage regulation, we looked at this as an electromechanical voltage regulator. And when we applied a voltage to the coil, we changed the field strength that was being generated, and that moved that switch, turning it off. Now, in a way, this is a sensor. It senses the change in voltage and turns off the switch. But of course, that's only one way of looking at it. Actually, it is intrinsic to the property of what we've built. We put more voltage in there, that magnetic field is going to get stronger, and it is going to turn that off, because it just must do. There is no sensing going on here, in the same way that there is no sensing when I turn off the light. But actually, there is also sensing going on here, because that field strength changes dependent on the voltage. So this is a bit of a crossover point. It's easy to see when we put a light switch off and on that no sensing is involved. It gets a little bit more complicated that no sensing is involved, but sensing is involved when you get to a device like this, where it's kind of a bit of a crossover, really, but it's still essentially the same thing. And actually, we are just making a choice about how we see it. We can see it as sensing, or we can see it as intrinsic. Either way, it's good. It's a way of talking about it. Now, when we're looking at individual things, like a light switch or a single mechanical relay, it's easy to see what I'm talking about, because you can see them, because they're big enough to see. But when I have a million little switches and each one smaller than a pinhead and it's encased in a black box, you can't see it. And when we talk about it as sensing something, it becomes mysterious. And that's where the problem arises. Because these things operate not because they're magical, but because they're built to operate that way. This thing both does and doesn't sense the current because the voltage, because it's built to operate that way. It's the same thing in a computer. A computer is nothing more than a million or a billion switches in the position of off and on. Depending on their position, they'll do something. that something is intrinsic to the property of the way the switches are switched. That's all there is. Now, it's often viewed that the first computer was in fact something called the Jacquard loom. Now, a loom works because you raise some strings up and down. You have all these strings running in one direction, and they're different colours. And you have another string that you weave in and out in that direction. Depending on where those strings in that direction are lifted, the colours will change. If I have red, green, blue, and I lift the green, I'll see the green. If I lift the two red, the red and the blue, I'll see the red and the blue. So that pattern depends on the position of the string. Now, a weaver will use that by pressing foot pedals to raise some strings up, then put the other string through in that direction, and you are weaving. It's a tremendously tedious job, it's a great skill, it takes a lot of time to do all of that stuff. Then this French guy came around and said, okay, all we're doing is raising strings, let's put a bar over with some holes, press the whole lot with my foot. Only where the holes are can the rods go up, and only where the holes are will those strings be lifted. Then if I change the bar, then I will change the pattern, and that's exactly what he did. And he made these bars out of card, actually. They were big card rolls, they would roll over the head of the loom. You just pressed your foot when a new card was in, and automatically you got the pattern, and that pattern was encoded on the cards. Now, obviously, there was no choice involved here, there was no sensing involved here. The thing did that because it was made that way. It could only do that. Even though we changed the card, we could change the pattern. So, in a sense, that was in fact the first program. But equally, in a sense, it was responding to the way it was made. All these things are. So when we get lots of things all put together and lots of switches, we start to talk about things like sensing and knowing. And that starts to introduce mystery and confusion, because how does something sense? How does something know? And that's the way it is with charge controllers. We're looking at a charge controller and we're talking about it sensing the voltage and changing this and changing that. The issue isn't about how it physically does it, the issue is about understanding how it knows. But of course, knowing is one of those things that's actually a bit of an illusion, and that's what I was illustrating at the beginning there. The light doesn't know that I've turned the switch. But equally, in another way of looking at it, the light does know that I've turned the switch. And so this idea of knowing actually is intrinsic to the build that we've actually made, the stuff that we use to do these jobs. Of course, there are many, many ways of doing a particular job, as we know. Well, I say that, but some people think there's only one way of doing it. It's not right. There are just many ways of doing it. If you think there's only one way of doing it, the perfect way, I am so sorry to tell you, but you're wrong, and you really need to rethink your position. Or at least, that's what I believe. Now, this idea of many ways of doing things gets even more confusing when people are trying to work out what it is they need to do. So you need to build a charge controller. Fantastic! And then there's many ways of doing it. Oh crikey, which one do you choose? And of course that pushes you into looking at those many ways, trying to build something from those many ways. And to me, that's upside down. To me, what you need to do is work out what job it is you need to do. Then you need to look at the ways that job can be done, and then choose an appropriate option for you to perform that job. So we change now our focus from looking at the many ways, which is just infinite actually, there's tons of them, to looking at the idea of the job. And of course that's exactly what Jacquard did. He looked at the machine and what the machine could intrinsically do, and then he created all of these cards because there were many ways to weave a carpet or a piece of cloth. But there aren't many ways to actually put that information into the loom. The loom is much more restrictive. And of course we want something that's much more restrictive. We want something that is a charge controller. That charge controller is only going to do a certain number of jobs. The jobs we wanted to do are the logic of the charge controller. Now we began by looking at voltage control, and we began looking at voltage regulation. That's what that mechanical thing was all about. It was starting to look at charge controllers by looking at one section of what the charge controller does. Because the charge controller obviously has a number of jobs, and we'll cover those later, but we looked at one job and then the possible implementations of that job. Now, of course, we did a mechanical version because that's what they used to do when this stuff first started to become important, because mechanical versions help you to grasp what's going on, in the same way that when I turn a light switch and the light goes off, it's not a mystery to everybody, we all understand what's going on. If we can look at something we can look at, we get a good understanding, but the job doesn't change. We need to do the same job. That is, we need to control the voltage going into a battery. Then it's a question of how we actually do that. Now, how we actually do that, how we implement that logic, is actually independent of the logic itself. Just because we use a solid state, or we use a mechanical relay, or we just use our eyes and a switch, it really doesn't matter. The job is being done by somebody or something. The job itself remains the same. So if I want to understand what it is that I need to do in order to build a charge controller, probably, or at least in my view, the worst approach is to go looking at things of trying to find the perfect answer. To my mind, the best approach is to look at what jobs that actual charge controller needs to do. Once you've sorted that out in your head, you can then look at how to implement those jobs. What you find people doing very often is telling you about the best implementation, what they think is going to work really, really well. And of course, that so quickly becomes confusing because they lose sight of the job itself. And then people who are first coming to something and have a mystery surrounding that something and don't really understand what the logic of the job is, and they focus on what other people are telling them, of course it's confusing. What we need to do, according to me, and the way I see it, is to work out what jobs the charge controller needs to do, and then how we can actually implement those jobs. So essentially, as I say, what we're doing is we're breaking down the job into what a charge controller needs to do, and then how do we implement what it needs to do. And of course, that's an innocent statement, but hidden in there is in fact the bone of contention, and that is need. Now, different people have different ideas about what they need. And when they get an idea about what they need, of course they're going to argue for it, because for some reason we make the assumption that what I need is what everybody needs. And of course that's just not true. People need different things. And when you break down into logical bits, you have the option of asking yourself, do I need to do that? And the answer may be no. Now, I think it's MPPT is the current all-star of solar charge controllers, and everybody tells you need it. Now, I'm not saying that you do or don't need it. I'm saying ask yourself the question, do you need it? If the answer is no, because your needs aren't being met by that, don't use it. But of course some people say to themselves, I need it, you must need it, therefore do this. And that to me is the wrong approach. So this breaking it down into blocks gives you lots of opportunities, but it will also create quite a bit of argument. There's not a lot you can do about that. Have a bit more faith in your own needs. If you understand the blocks and your needs, you're going to find solutions. We made a generator and we connected it to a voltage regulator, we smoothed the voltage and charged a battery through a BMS with it and then put it on some load. And in order to do that, we used this. It's a pre-bought voltage regulation board. It's quite good. You can take a high voltage in and put the desired voltage out, and you can change that by twiddling that little knob there. But at the time I said, well, just buy this, because these things are amazingly cheap. But it is a black box, and I hate black boxes, so I always want to know how a black box works. So, big question. How does a voltage regulator work, and how do you go about building one? Now, voltage regulators were initially electromechanical devices. They were in fact just relays. Not too dissimilar to this, which is a household relay for electrical supply. Now you very rarely get them in one relay configuration. Mostly you can still buy them for things like vintage cars and tractors, that sort of thing, in a two-relay configuration with a voltage regulation relay and a cut-off relay. But you'd also get them in a three-relay configuration where you have current overload protection, voltage protection and circuit cut-off. Now if we have a look at the circuit diagram of the cut-off relay first, what you can see there is an iron core with a coil around it, and it connects a generator to the battery circuit when the generator builds up to the desired value. It also disconnects the generator when it slows down or stops. That iron core is magnetised to pull down on a hinged armature that you can see against a spring. When the armature is pulled down, a set of contact points closes and the circuit's complete. When the magnetic field is broken, like when the generator slows down or stops, a spring pulls that armature back up, breaking the contact points. The voltage regulator is just another iron core operated set of contact points, but obviously this time they're in the closed position, and it's used to regulate maximum and minimum voltage at all times. This circuit's also got a shunt circuit which redirects the electrical flow, going to ground through a resistor and is placed just ahead electrically of the points. When the points are closed, the field circuit takes the easy route to ground. When the points are open, the field circuit must pass through the resistor to get to ground. The field coil on the generator is connected to one of the voltage regulator contact points. The other point leads directly to ground. When the generator is operating, battery low or a number of devices running, its voltage may stay down below that for which the control is set. Since the flow of current will be too weak to pull the armature down, the generator field will go around through the points. However, if the system is fully charged, the generator voltage will increase until it reaches the maximum limit and current flows through the shunt coil will be high enough to pull the armature down and separate the contact points. Now they repeat this cycle time and time again with the points opening and closing somewhere between 50 and 200 times per second, and that maintains a constant voltage in the system. Of course, it's the same with the cut-off relay as it is with the voltage regulator. We can adjust the tension on that spring on the contact points so that we can therefore adjust the voltage that it will open at. See, in a three-coil setup is this, where we have a cut-out relay, a voltage regulator and a current regulator. Because although the voltage is now being controlled, it is still possible to have too much current flowing. And in the current regulator, there's a few turns of thick heavy wire connected in series with the armature. Now again, when the current rises too high and the magnetic field gets too strong, a set of contacts is opened and it disconnects the generator. The advantages of a mechanical setup is that the mechanical system itself both senses and switches. That's what a solenoid does. It senses the voltage and switches at the same time. That on-off switching, which if you want to think of it, is kind of like pulse width modulation, but that on-off switching is the core of current and voltage regulation. Now in modern day electronics, where we get this beautiful little board, what they do is they separate the sensing and the switching from each other. The sensing is usually done through a resistive network so that we can bring down the voltage to the logic voltage level, because even though we're pumping out sort of 12 to 14 volts, and in some generators far more than that, this stuff can stand somewhere between 3.3 and 5 volts, so it's too high. So we use a voltage network to bring it down to a range that the electronics can sense it, and then we use a transistor as a switch to switch it. So the first thing you need is a simple voltage divider circuit to scale the possible output voltages into a ranges that the Arduino can cope with. That's between 0 and 5 volts. It's just two resistors in series, and in the middle you take the voltage from the Arduino, and that goes to pin A0. So that's the sensing circuit, and this is the control circuit. All it is a switch to turn on and off the field winding. You just use a large transistor mounted to some random bar as a heatsink, and you connect the output to the field winding through the transistor. It's just a solid state electronic on-off switch in the same way that the solenoid worked. The Arduino gets connected to pin 13, and pin 13 has its own LED so we can see it flickering off, and here's the code to control it. Now if the output is below the 14 volts, which is the threshold, then the field winding is turned on. As the engine spins up and the alternator goes up beyond the threshold, then you turn it off. Once it goes past the threshold, then the Arduino will turn off and the magnetic field will shrink and the output will dip below the threshold, and then the Arduino will turn it back on. So it's basically just switching on and off really fast, and that on and off fast switching in link with the engine speed is what the voltage controller does, whether it's electromechanical
so whatever
or
generator
electrical.
you're using, whether it's a homemade one like this one, or a converted brushless DC motor, or a universal motor, or an alternator, voltage regulation is accomplished the same way. You switch the generator in and out depending on the voltage the generator is producing. And you can do that either electromechanically, where you're combining switching and sensing, or you can do it electronically, where you separate the switching and sensing and use a transistor as the electronic switch, or you can buy yourself a black box board and make it all very much easier for you. Anyway, I hope you enjoyed the video. I hope it helped. Thank you very much for watching, and please do remember to like and subscribe.